Well, hello everyone, and welcome back to the ESPM seminar series. I'm Nick Mills from ESPM, and it's my pleasure today to be able to introduce Wayne Getz, our seminar speaker for today. Wayne, although retired, is still very active and is a former faculty member of ESPM, and is now a professor of the graduate school. And I've known Wayne for many, many years, of course, since we've both been on campus for some time now. And Wayne, of course, is particularly active as a theoretician interested in applied questions in population biology, particularly with application to epidemiology and to wildlife conservation. And looking back over Wayne's career on campus here, every 10 years or so, he seems to pick up on something new. So when I first came to campus, well, I think when Wayne first came to campus, it was all about harvesting and sustainable yield and fisheries. But by the time I came to campus in the 1990s, he'd switched to honeybees and looking at odor signaling and kin selection and so on. But it was really in the 2000s that he blossomed, because he moved away from insects and moved into wildlife conservation and disease ecology, which really was a wonderful turn of events, because I've never known somebody so productive in this area since that time. And once we got, of course, beyond the 2000s to 2010, Wayne took on yet another direction, developing platforms for modeling, developing software platforms for modeling, expanding his interests in disease ecology to HIV, measles, and now into COVID. And movement ecology was another big area in which Wayne was one of the pioneers. So he's had a tremendous career on campus, and you would think retirement might slow him down a bit. But that doesn't seem to be the case whatsoever. He is still very active and very productive. And so now that we're moving into the 2020s, I'm just wondering what is the next direction that Wayne will pick up and pursue for the next 10-year cycle. So we've had a lot of fun, Wayne and I, over the years, and it's really my pleasure to be able to introduce him to those of you who haven't had the chance to know him so well. And I don't want to take up any more of Wayne's time in presenting his seminar. So I hope you'll all join me in welcoming Wayne back to the ESPM seminar series. And he's going to present a seminar for us today entitled A Versatile COVID-19 Web App for Epidemiologists and Policy Analysts to Manage Outbreaks. So over to you, Wayne.
Thanks, Nick. That's very kind of you to give me such an introduction. I must say that when I came to Berkeley, it was to work in integrated pest management, not on fisheries harvesting, which I did before I came. But it's true, I got involved in insects other than pest management. And even though I'm working with big mammals in Africa, which is one of my passions, I still have great fondness for honeybees. So there we go. Can everybody see this? And let me start my presentation. Okay, so just checking everybody can see this. We're on track, is that right?
Yes, yes.
Okay, great. So what I'm going to talk to you today about is another one of my interests, which is really disease ecology, but being a disease ecologist, you keep getting dragged into doing human work. I try to avoid doing human work, but ultimately when you're short of a few dollars, that's the place to go and get some money. So here I am working on COVID, which was a place to go and get some funding for my group, but also a very, very important problem and a tragic problem in some ways, and a totally and utterly mismanaged problem in the United States. The title of my talk is A Versatile COVID-19 Web App for Epidemiologists and Policy Analysts to Manage Outbreaks. And I'm going to talk about applications of this web app to data from England, South Africa, and Israel. Nick mentioned that I've been involved in building a website for model building, which kind of is along the lines of the other modeling app built at Berkeley by George Oster. And the reason why we went on a slightly different path is because we were also interested in doing agent-based modeling, which the Berkeley Madonna doesn't really cover. And in working on this, I've been working with Richard Salter. So it's been a very productive relationship that I've had with Richard over the last almost decade. Richard is a computer scientist from Oberlin College, also retired now. And so I have to confess that my interest is in modeling and analysis and mathematics. And when it comes to actually coding and programming, I'm rather useless. Fortunately, I got two great postdocs with me at the moment, Ludovica and Nir. Both are outstanding coders, and they've been working on this problem with me as well. So moving forward, the overview of my talk is, first I'll discuss and provide a COVID perspective from the point of view of pandemics over the past 1,500 years. So certainly pandemics are nothing new to humanity. And by some of the previous standards, COVID is by no means near the worst of them. Then I'm going to talk about, some of you may have heard of SEIR models, SIR models, or SEIR models. I'm going to show you how ubiquitous they are and how they've been used across the board by a number of scientists to analyze COVID-19 problems all over the world. Then I'll talk about a model that I developed for COVID in particular and why it's specific to COVID. And then we'll talk about the web implementation of this model with the help of Richard and the postdocs that I mentioned. And we'll talk about the application of the model to data from Israel and South Africa and England. So let's take a look at COVID-19 in historical perspective. So some of the great plagues of the past 2 millennia have been bubonic plagues. There's the Justinian plague, where 5 million died in a population of 0.2 billion at the time, just to give you some sense of mortality or relative mortalities. Then the big one was Black Death, which was the scourge of Europe and parts of Asia from 1346 to 1353, where approximately the best estimate to date is on the order of 25 million died in a population of close to 500 million people at that time. Also an exceptionally high death rate. Cholera, of course, has been important throughout the past several centuries. We're currently in the midst of the 7th cholera pandemic, which is quite a drawn-out affair, and started somewhere in Indonesia around the very early 1960s, and then spread to Bangladesh, India, the Soviet Union, Guinea, and the Americas after that. And it's currently infecting approximately 3 to 5 million people annually. The 3rd cholera epidemic, which was around 1852 to 1860, led to the death of about 1 million people in a population of 1.2 billion. And the sixth was also an important outbreak around 1910 to 1911, which led to the death of 0.8 million in a population of close to 2 billion people. Of course, the one that we've all feared have been influenzas, and we were all worried for a repeat on the so-called Spanish influenza around 1918 to 1920, in which there were an estimated 20 to 50 million people dead. It's very difficult to estimate the actual numbers, and that was in a population of about 2 billion. So we're not anywhere close to that at this time, and hopefully we won't get close to that. We're a little bit closer, I guess, to the Asian flu or Hong Kong flu epidemics of 1956 and 1968, where a couple of million people died in a population of approximately around 3 billion. And then the big one in our time has been HIV. The peak of the HIV epidemic is roughly from 2005 to 2012, although the earliest cases probably go back to the 1970s and maybe even the 1960s, but are not identified as such. And there we have 36 million people globally dying from HIV in a population of somewhere between 6.5 and 7 billion throughout that period. So this brings us to COVID at the end of September, where the population of the world is moving on to 8 billion, and there have been about 35 million cases worldwide with more than 1 million deaths. And the US has approximately 7 million of these cases with 0.2 million deaths, although the US population is less than 5% of the world population. Now, people have been modeling epidemics for over 100 years now. And the most important of these have been the so-called compartmental models, or the SEIR model. And Wikipedia, as long as it's not a controversial subject like politics or some of the social science subjects, is pretty good for getting scientific information. And you can go there and read about SEIR models. The SEIR class of models is you have a compartment of susceptibles, a compartment of both infected and infectious. There's no discrimination between those two classes that has been made in these models, and then recovered. So the population is divided into these three classes, and you introduce an infected individual, and then the epidemic can start, and the susceptibles, the infection or pathogen can be transmitted to the susceptible population, and then the individuals will be infectious for a period, and they'll either die or recover. And you can, if latent periods are important, which they are in certain diseases, perhaps not so much in influenza, which might have a latent period of just a couple of days. For COVID-19, the latent period might be 4 or 5 days. But here what you see is that if you start off with a susceptible population and you introduce an infected individual, you might ask, what is going to happen? When will the epidemic burn out? So the epidemic takes off in an exponential type of phase. It passes a maximum point and then it starts to wane. And the epidemic will burn out when the proportion of susceptibles in the population has fallen below a critical level by going from the infectious to the recovered stage, where you assume that the recovered have at least some temporary immunity. And this threshold level inversely scales with the risk of transmission. So some pathogens are highly transmissible, like measles, and some less so. Initially with COVID, it wasn't clear whether it was highly transmissible, and it only became clear, I guess, towards the end of January, February, early February, that there was an important problem with it. And also epidemics can be controlled by reducing the transmission through behavioral changes, such as social distancing. And then finally, you can take individuals from the susceptible directly to this immune class without having to go through the infectious class if you have an effective vaccine. And if you can get enough people vaccinated to the so-called herd immunity level, then you can help extinguish the outbreak. If we look at the growth of the application of SIR models or SEIR models in epidemiology, in order to understand this, I went to the Web of Science and I searched on all records involving epidemics and SEIR models. And I came up with 873 records. So the earliest of these models, there are very few before 1996. And then up to 2004, when we had the SARS outbreak, the number of papers that involved SEIR modeling was fewer than 10 a year. Then after that period, it increased, coming to around 50 or so a year, a decade later. And then by 2019, for the last few years before that, there were on the order of 75 papers a year. Now, up until August, the end of August, there were over 110 papers, and I'm sure there'll be well over 200 papers this year that have used SEIR models to model COVID outbreaks around the world. If we have a look at the early papers in the field, because this only gives us a view of the early papers, papers have to be submitted, they have to be published, people have to cite them. And so it takes a while for these papers to get a citation. But the earliest papers came out of China, one from a cruise ship, one from Italy, China, Spain, and so others. But of course, we're going to see a lot of analyses coming out now from all around the world. If we have a look at who's doing what in the US in terms of trying to predict and use mathematical models of the SEIR type, the most important group doing this is the Institute for Health Metrics and Evaluation at the University of Washington. It's an independent global research center. If you go to their website, you'll see that you can play around there and you can look at projections. And they'll update these projections, let's say on a weekly basis or more often. I'm not sure exactly how often they do it. And you can look at other statistics and you can look at projections they make. Here's a projection from sometime in October, and they're looking under 3 different scenarios, one in which individuals are wearing masks, one in which people are easing up on their social distancing, and one which reflects the current situation. And you'll see the results of their analyses cited, and they have predicted, I guess, by the end of the year that there'll probably be over 400,000 deaths in the US. If you go to the CDC, they do a compilation every so often of people contribute their forecasts coming from all these different places. So here we have University of Georgia, North Carolina, MIT, and so on. Here's UCSD and UCLA. There's no Berkeley in here because there's nobody at Berkeley contributing to this particular effort. And they will update every so often, and they'll have a look at a consensus model. So these are the various models, and then they'll get a consensus point of view for the number of deaths, the combined forecast, and so on. And you can see that there's a broad array, and people are perhaps using different parameters and slightly different models. And it's hard to get a consensus of what's going on because there's a number of other things going on behind the scenes that make the SEIR models rather complicated, because there are a number of assumptions inherent in those models that are obviously don't apply, like homogeneity of population, everybody behaving the same way, and so on. So if we look at if we continue with forecasting in the US, there is this website, COVID-19 Simulator, that you can go to. And it's also an SEIR model. It uses the data that comes from the Johns Hopkins site. You can carry out in a very limited way some of your own simulations, but you have to use data that either is the US national or state level projections. You use the data that they supply for you. You can carry out side-by-side state-level comparisons, and you have a limited number of scenarios that you can look at, like a minimal restriction scenario, a stay-at-home scenario, and an extreme lockdown scenario. So there's really not much in the way for, let's say, people who don't have modeling skills or aren't able or don't have a strong enough background to build their own models, but who'd like to do something. So these may be people who are responsible for healthcare decisions in the counties, in other state offices, and maybe at the federal level as well. And also around the world, there's nothing that's available. So of course, in countries like many of the European countries, they have their own modeling groups. But if you go to some of the third world countries, there may not be enough expertise to really carry out the kinds of analyses that they would like. So one of the goals of our website was to build a website that was rather flexible and versatile, and allowed epidemiologists and managers around the world to analyze various kinds of policies and explore different options. So we also wanted to provide something, a tool for policymakers and health officers who really don't have this modeling and epidemiological expertise, but yet need to make decisions about should schools be closing, should people be social distancing, at what level should they be doing this. And so we felt if we could get a tool and without too much training, maybe an hour or two's training to get people used to the interface, that they could actually begin to use this website to model outbreaks in their local areas. So we also needed a model that included things like social distancing, contact tracing, and quarantining, that could account for the fact that there may be new therapeutics so that mortality rates could be going down, and also to help plan vaccination rollout programs. So we felt like it's important to try and get something out there that people could use. In order to do this, we had to take the SEIR model and expand it to make it suitable for an analysis of what's going on with COVID. So, for example, if you take the basic SEIR models, susceptibles, exposed but not yet infectious, infectious, and then recovered with some immunity, our model considers that individuals may have made contact, but some may not succumb to the pathogen. If they do, they go on and have a latent period, which is the same as the E class in the SEIR model. And then what is important are asymptomatic transmission. And so asymptomatic can be pre-symptomatic if it goes on to I, or it can be asymptomatic and then go straight to recovery. So we had to allow for these two different pathways. And having an identified contact class where individuals may or may not get the disease allows you to more efficiently plan contact tracing and quarantining, which the SEIR model doesn't have. Then we also added what I called a response sequence that matched this SCLAIV sequence. The response sequence are individuals that you move out of these compartments into the response compartments. In the response compartments, you have individuals who are socially distancing themselves, and hence you have lower rates of transmission for all individuals who are sitting in these classes. And then you have a VR class, which is a vaccination class, and the V class is actually like the recovered class, although sometimes in an SEIR model, this is called a removed class, which includes those who are immune and those who have died. And then what we did is we looked at drivers. So for example, if you social distance, you move from S to SR. If you're in SR and you begin to relax, you move back into S. If you're contact tracing, and you become isolated. So if you're doing contact tracing and you have a look at individuals who have been in contact, but we don't know whether they've got them, then you put them in this contact tracing response class, and then they might be infected or they might go back to the socially isolated class, and then they may relax again. So we allowed for these so-called drivers. There's a surveillance driver. Now, surveillance is important because one of the big things is we don't really know how many people are infected, especially since asymptomatic individuals are not necessarily identified. So depending on surveillance, and surveillance here relates to the intensity at which you test individuals to see if they're infected. So if somebody's been in contact, you can test them to see if they've made it out to the asymptomatic class. And if they have, you may isolate them. There's also, of course, if somebody is ill, you isolate them and you treat them. There's the social distancing. There's a contact rate reduction driver, which tells us if you're in the social distancing class, how much has your contact rate gone down? There's social relaxation, which means you stop your social distancing and you start to resume normal activities, and quarantine and response drivers. And also, one of the things we wanted to do was not treat these rates as constant, but treat them as switching functions. So for example, a switching function has an onset time, the point at which it reaches half the maximum value, and then an asymptotic value. And so as individuals are in, say, for example, the susceptible class, then social distancing switches on as a process and becomes a maximum, and the same with social relaxation, it switches on as a process. And it's the same with surveillance. Surveillance starts out at a certain level, and then it may switch on as we increase testing intensities. So here's the website that we built, and everybody's welcome to go to the website and play around with it. You click to enter, and you come to this data page. You can press default settings and import a set of default settings. You can import a set of incidence and mortality time series. You can save the settings, you can clear settings, and you can put in values on, if you want to fit your model over a particular sub-interval of the time series, you can put those numbers in here. And you can also control your simulation range. So the mortality and incidence data just are fed in as two strings of numbers. And this is daily rates. So this is 2, 3, this is the daily incidence, and this is the daily mortality. And you have a set of default parameters. The model talks about total population size, contact rates, infection rates, latent periods, infectious periods, but then there are these other periods related to if you're in contact and you succumb, or if you're in contact and you thwart. If you thwart it, you go back to the susceptible class. If you succumb, you go on to the latent class. And then there's also initial conditions. When you start out, we don't know how many infectious individuals there are in the population at the time we start the simulation, or how many individuals have been exposed, so we have to fit those as well. We fill this out and we save that file. And then we come to the optimization page. And sorry, let me go back to the optimization page. Something's happening here. I'll come back to the optimization page. This is the forecasting page. And we also have a page where you can fit your model using maximum likelihood, using Monte Carlo Markov chain methods. So let me illustrate how we used this website to study these 3 case studies. The first is the Israel epidemic. And what I'm going to give you is an analysis that was conducted up to about a month ago. We've submitted a paper. And if you look at Israel, you see that there was an initial phase of early exponential growth. Then there was a turnover, and it was almost extinguished, but not quite. And then it rebounded for a second wave. So the initial phase we call the outbreak phase, where we estimate the basic parameters. Then the second phase is where social distancing set in, and we can estimate some of the social distancing parameters. Then the third phase is when social distancing was relaxed and there was a rebound. And then there was a post-relaxation phase, and I'm going to discuss that in a little more detail in a minute. So we started off by fitting the first 14 days of the epidemic using our web app. And you'll see how this works in a minute when I give you a live demonstration. We then said, okay, let's then fit the first 35 days. So we got the basic fit for the first 15 days, but then social relaxation sets in. So then we play around with some of these social relaxation parameters, and I'll show you how we do that. And then we can move on and we can model in more detail some of the extended data sets. So let's first take a look at how the web app works. So I'll give you a live demonstration. Can everybody see this web page?
Yes.
Okay, thanks. So here it is. I can click it to enter. I can use default settings, or I can go and I can load some settings that I've saved, like this. And I have a set of values. Then I can go to the optimization page. And I can choose to, over here, I'll fit the first 30 days of data. I can fit the contact rate parameter. I can fit the initial number of individuals who've been exposed, contacted, but not necessarily go on to get the disease, the number of individuals who are infectious, and so on. So I have 4 parameters here that I'm going to fit. I could fit any other parameter I want. I'm only going to fit 4, and I can start the optimization process. And it's running, and you can see these 4 parameters are being fit over here. At any point, I can stop the optimization to see how I'm doing. And you can see I'm beginning to fit it. And then I can go back and I can continue this until what happens is that it'll converge to the best fitting solution. And you see that I've got a lot of options here for fitting all the different switching functions. And we haven't got time for a full demonstration, so I'm going to just continue with my presentation. So I'm going to stop this, and I'm going to go back to my presentation. Okay. So here you can see with the Israeli data, we fitted the first 15 days, then the next 30 days. And we did 2 additional fits. In the first one, what we did is we switched on the social distancing parameters, and we estimated the time at which social distancing is switched on, the initial level of social distancing, the final level, and the midpoint at which it switched, and we got this particular fit over here. You can see this fit begins to fail because there's a resurgence over here. So in order to get in that resurgence, what we did is we, in addition to fitting social distancing, we also fitted social relaxation. And you can see that over here, we get our exponential phase, we get social distancing, and we get social relaxation. And we get a pretty good fit, as you can see. And we can continue fitting this model, and we can fit things other than just social distancing and social relaxation. We can also fit the mortality rate. So by fitting the mortality rate to the mortality data and the social distancing and the other parameters to the incidence data, you can see that what happens over time, and I'll show you some curves, is that the mortality actually goes down because I guess hospitals and doctors become better at treating the disease. So we can actually estimate how well that's operating. And so we get social distancing switched on. This is the social distancing curve. And sometimes later social relaxation comes into play, and the daily mortality rate goes down dramatically. And in fact, in Israel, they've been very good at keeping mortality very, very low. We haven't been nearly as good at doing that in the US for various reasons. We can also do a Monte Carlo Markov chain projection. And we have a page for doing that. And you can see that this is the first phase. Then we got the social distancing, the social relaxation. And now stuff begins to happen in the post-social relaxation, where different groups are trying to open up the economy. Maybe kids are going back to school in some areas, but not in others, and a lot of stuff's going on. And so we can make a projection. If things continue as they have, beyond, so what we do is we fit these data over here, and then we fit the data up to this point over here, using Monte Carlo Markov chain methods, and then we get a projection, and we can project out further in time, and we have an opportunity here to project as many days into the future as we want to. So we have a lot of control over this projection process. And I can give you a live demo of that again. So we can go to the website and we can enter it. And then I can go to the forecast page, and I can do a run over here. I think, let me just make sure that I've read in the data. I don't seem to, let me go back to the settings page, load for the forecast. I'll load the data in. I'll go back to the forecast page, and I'll do a run. And so here you can see that you can do many runs because you can do stochastic simulation. I'm going to stop this if I can. And you can see that I fitted the model up to this point, and then from this point onwards, I got various options, and I can change, I can switch on social distancing, for example, and I've got an MCMC fit that I've got to that, and then I can do, I can run it once, and if that social distancing persists, sorry, yeah, this level of social distancing that we have over here persists, then the outbreak will be extinguished. So let me go back to my presentation. And So now I'm going to fit the South African epidemic. The South African epidemic is rather different from the Israeli in that you only have one peak and then coming down. This is by the middle of August. Again, we can fit the early stages of the epidemic. We can then fit a longer time series that includes some social distancing. We'll see that this is not a particularly good fit unless we include fitting changes in surveillance. So as the epidemic's ongoing, surveillance efforts change. And we can do even better if we add a social relaxation parameter that will tell us how to move beyond this particular point. And so we can do this, and we can fit the various drivers that we have. Or we can fit all 18 parameters simultaneously. And again, we can fit it out to a certain point, and then we can do some projections. Now, I'm going to come back to these to see what's happening in the month since I did this analysis. But before I do that, I'll finally look at the English outbreak. The English outbreak has a peak and seemed to be coming down to have some level of control. So I fitted the first 2 months of data, and I progressively fitted different drivers. You can see here that this is quite a good fit, but at this point, it doesn't fit very well. So we're going to go beyond that point, and we're fitting the basic epidemic parameters, social distancing, we're fitting changes in surveillance and social relaxation, and we can fit mortality as well, and we can get surveillance has gone up, social distancing started at this point, social relaxation crept up or, during this period. You can see it's ongoing, and virulence has gone down, which translates into an improved ability to ensure that mortality rates are lowered. And so we can do a simultaneous fit of all those as well. And I'm going to come back to these three and have a look at what I call the conclusion. So in Israel, what we found is that a 5-fold reduction in social relaxation levels at the beginning of July confined the incidence at this point. And the question is, has this 5-fold reduction in social relaxation levels that were happening at this point, are they going, what is going to happen over here? Are we going to keep steady? Are we going to be able to bring it down? If we bring it down, it means that social relaxation levels, again, have dropped and more social distancing is taking place. So we can say how much social distancing is needed at this point to bring the forecast down. So we can do that analysis. But if we have a look at what's happened in Israel, here's the first peak, which corresponds to this peak. Here's the second peak, which corresponds to this peak over here. And we forecast out that if things remain the same over this period and persist, this is what would happen. We'd be somewhere between 1200 and 1750, but you can see that there's been a tremendous outbreak in Israel. In fact, it was so bad that just before the Jewish holidays, or on the start of the Jewish holidays, the New Year in Israel, they said they're going to lock down for 3 months because it's out of control. And Israel has one of the worst outbreaks per capita in the world. If we look at the South African epidemic, we had analyzed it to this point, and we fitted these particular curves. And in fact, if you persist with these curves, we were going down, and you can see that it's continued to go down. So in South Africa, things have been brought under control, and we don't know what's going to happen in the next several months, but certainly the situation looks good compared to what it was in the middle of July when South Africa rose to be the 5th largest outbreak in the world, even though it was much smaller than the other countries like Brazil, India, and the United States that had the largest outbreaks. In England, let's see what has happened. In England, we predicted that surveillance up to this point, social distancing, social relaxation, and virulence. And we fitted this curve, and it's not clear at this point whether this was under control and being contained. It looks like it was going to start rising again, but we hadn't seen enough data to know what was going to happen. And as you can see, there's been a second outbreak. Now, this is the UK data, which is very similar to the England data, but includes England, Scotland, and Wales, and Northern Ireland. And you can see it's actually worse than the peak at this point. So in the UK, they haven't been they were initially rather successful, but I guess people got tired and started to socially relax again and lose vigilance, go back to the pubs. And it's not clear what's going to happen now. If they don't take strong action, then it's going to get even worse. So something has to be done. So the general conclusions are that we feel that this web app that we've built allows people who have very little or no modeling experience and no computer coding expertise to use this tool. We feel like if we sit down with somebody and take them through the use of the tool for a couple of hours, we can get them using it, and we can also guide them through it. And they can get within a day, certainly, on using this tool on their own and analyzing their own data. And to facilitate its use, we're upgrading it all the time. We have an information button. We have an enable information button here, so that if you mouse over different parts of the website, explanations will come up on how to use the website. And thank you for joining us. Thank you for listening, and remember to stay safe. And I'd be happy to take questions. So I think I should stop sharing. Right. Okay, so
thank you very much, Wayne. We can coordinate the questions if you wanna use the chat or raise your hand, or you can go ahead and ask the question if you prefer.
So Nick has a question.
Thank you, Wayne. That was very interesting. You've obviously put a lot of time and effort into developing this app, and it seems to be very versatile and be able to answer some interesting questions that are of importance in setting policy about social distancing in different regions of the world. You know, one of the things that I always come back to is the setting that we now have, the need for social distancing, and the suggestion that you have sufficient social distancing if you keep 6 feet apart.
Right.
Has your model got any ability to look at how actual distancing can influence the social distancing element of these models, or is that too much detail to have in the model?
Right. So, I mean, I think that's an important question to understand the answer to, because a lot of people maybe don't realize how inadequate our models are and how they depend on reliable data and what it all means. So a model at this level does not take anything like that into account. And you have this concept in SEIR models and all these classes of models of a contact rate. And if you try to search the literature and really try to understand what's going on, you'll see some studies where people, you know, who are interested in how aerosols move around and how virus particles move around. And it's a completely different kind of sphere of analysis and kind of model. But if you're going to implement it and you're truly going to try and relate a contact rate in your model to something that you could measure, it has been suggested that for COVID-19, a contact rate means that you will have been within 6 feet of an individual for at least 15 minutes. However, it says nothing about wind conditions, temperature, humidity, or all the other factors that are important. So this is a huge gap. And so you kind of have to infer what contact rates really are by doing experiments. And you can't do these controlled experiments. They're not ethical. You can't say, okay, here's a group of 30 people, spend so much time in this proximity to an individual who's infected, and let's see how many of you get infected. And, you know, do experiments like ecologists would do with different treatments. You're there in this distance for this amount of time. So there's none of that. So all this stuff is incredibly fuzzy. And so it's very different. That's why projections that you talk about in summer conditions are completely different in winter conditions. That's why colds and influenza are winter diseases rather than summer, because people are indoors, temperatures are different, proximity rates and time spent close to individuals. Are you in a building with an efficient air conditioning and HEPA filter, or are you in a stuffy restaurant? Yeah, so you can see that it's a horrible situation. And these models, at best, you know, fit very broad averages for a particular population group doing a particular thing. So for example, a model that applies in New York won't necessarily apply in Atlanta, or I should say parameters that apply in New York won't necessarily apply in Atlanta. What are these parameters? These are things like contact rate parameters. There are other parameters, which are the latent period of the disease in an individual, the infectiousness. These are things you can measure and that are likely to be stable and relate more to the pathogen, but it also, there's an individual variation, as we can see. Why are some individuals asymptomatic and others are not? So there's incredible variation, and we're averaging all that stuff out. And this is why these models, they provide the best way, the best estimates that we can get, but at the same time, we have to understand their incredible limitations, and especially if there's a lot of spatial structure. That's why we try to apply our models. You know, applying our model to England is better than applying it to the UK. Applying it to London is better than applying it to England. And you can't apply it to the US. You can only, what we're doing now is we're trying to apply it to metropolitan areas in the US, different metropolitan areas, because they form a more homogeneous group than the country as a whole, or the state of California. Don't try to mix Los Angeles and San Francisco into the same model. It's just not going to work.
Thank you. We have one question in the chat by Pranav Pandit. Say, thank you for the great presentation. I am Pranav Pandit from UC Davis. I think you told this, but I missed it. How many parameters do you think the model is able to estimate at a time?
Okay. Yeah, so this is an interesting question, because estimating parameters depends on a number of things. And the fewer parameters you need to estimate and the more data you have, the better. Now, there are lots of parameters. Fortunately, we have a lot of data. But for example, in the first 30 days, we just tried to estimate the basic exponential outbreak parameters. Then during the social distancing phase, we tried to fit the social distancing driver parameters. There's a lot of correlation and linear dependence among parameters. So for example, if you estimate, it may be that the real dimension of the model is much lower than suggested by the number of parameters you're fitting, because if your contact rates go up, then the infectiousness per unit contact will go down in order to get a particular transmission value. So transmission transmission scales with contact rate, and it also scales with probability of transmission per contact. And so if you underestimate one, then you might be overestimating the other. So there are other things to look at, and what you can look at is the proportion of individuals that are infectious at any period or asymptomatic or are in the social distancing class. And it may be that a model, if you move the parameters around a bit, as long as you do it in a way that reflects their linear dependence, you'll get a very similar projection. So it's a huge problem, and but at the same time, what we're trying to do is we're trying to do comparative analyses with the model. So we'll have a look at the exponential growth rate in different metropolitan areas and say which does the model predict is the highest. Social distancing, which one had more intense social distancing? Was there more intense social distancing in San Francisco versus Los Angeles versus New York? So the model will be good, even though you've got a lot of parameters and you've got this problem of collinearity and fitting parameters. We should be able to get some way of exploring those questions and looking at different metropolitan states, metropolitan areas and the outbreaks, and say, okay, in the ones where there was higher social distancing, let's go and look at some big data on mask wearing and say, we find a good correlation between what the model says about social distancing switching on and mask wearing. So then we can find a correlative, but maybe we can kind of jump the gun a little and say it seems to be causal here, that masks help social distancing.
Mm-hmm. I have a related question. I don't know if these models can handle uncertainty in the data, given these are reports from governments, right?
Yeah.
I know that some countries changed the way they report, and only midway through the pandemic, they decided that only if there was high certainty that was a COVID death, so that they could tweak their. Yeah. So does it handle that?
Well, there's different things. So firstly, we have an observation process that's surveillance. So the observation process can handle that uncertainty. We also have the ability to project using demographic stochasticity. So we can do some projections with that level of stochasticity. Also, we can project using uncertainty and parameter estimates, having done Markov chain Monte Carlo estimates. But I would say that there's a lot of noise in the data, for sure, and you can see it. And in fact, we're fitting a 7-day smoothed, but we're lagging the smoothing. One thing I haven't understood is most people don't lag it. They smooth around the center. So you've got 3 days ahead and 3 days behind. But if you look today at who's got COVID, the lag comes from the past where somebody got it 3 days ago and then he reported today. It's not that they're getting it in 3 days' time and it's reported today. So I haven't understood the smoothing process that goes on at all those websites. But we do a 7-day lagged smoothing because there's a very, very strong signal, so that on the weekends everywhere, rates can be like half the rate of the midweek rate. So there's a lot going on in terms of reporting problems. And this is where I fault programs that we could have had in the United States on information coming out from the CDC and the federal level on how to collect and report data. I don't see any emphasis on data collection protocols. So what we've got is enormously dirty data, and we could do much better than that. And nobody's bothering to do at a national level kind of a protocol, everybody collect data in this way, please. And if they had this program was being run by ecologists, we could do much better at getting good data, or an environmental scientists, because they don't know. I mean, everybody's running around like chickens with their heads cut off. Governors are doing stuff that they have to do. People are phoning their offices. And there isn't a task force, which should have been set up at the federal level, should have been set up by CDC, should have informed all the counties on how you should collect and report data for this COVID crisis. And it hasn't been done. Mary.
Wayne, just on that, that was my question. I was wanting to ask you, is there any move? Was there any move by the University of Washington and the other leaders, academic leaders in this, to just do a shadow cabinet to make a consortium that wouldn't involve the government at this point, and could pool data, could pool suggestions for how to measure things that you can't ethically experiment with humans, but you might be able to, you know, put filters up at various distances, and
yeah,
and a repository for parameters and data.
So there may have been a lot of different efforts to do things, but they're all very local because nobody has the authority to scale. Oh. I went to a talk, you know, if you look at testing, if you roll out school programs and you put students in pods of 20 at a time, and you do pooled testing of 20 individuals, you can identify when that pod has an active infection in it. You can cut down, you don't have to test at individuals. And there are people who've got there are really smart people all over the United States who can do these designs and who are doing these designs, but they're doing it for local groups. They're either doing it for school district, or they're hired to do it here, they're hired to do it there. And this is where the national level has failed. And so if somebody wanted to form a shadow cabinet, you know, they would have to get funding, they would have to be able to scale it up. And in order to do that, it might as well be a federal implementation of a task force, because that's what it would become. So you're saying, you know, should there be a ground, sort of a ground swell to develop such a thing, or should the leadership have come from the top? Well, the groundswell takes too long and it's too difficult. The leadership should come from the top. It should have come from CDC. Yes. I think we had a big failure at CDC, but we've had a big failure at CDC because it's been politicized and everybody's trying to keep Trump happy by not giving the messages that he doesn't want to see. And this is where we have utterly failed. In February, the federal government should have set up a task force, what I call a war cabinet. Yeah. This is a war.
Yeah.
And you need the generals. And the generals in this case are the best scientists. And you need them from epidemiology, and you need economists, and you need people who can integrate and think at a systems level. If you have a look at what Sweden did, Sweden didn't shut down everything. And they were criticized for having higher mortalities than the Norwegians and the Danes and the Finns. But in retrospect, they seem to now be doing better because their economy was never shut down. Now, I don't know to what extent they really coordinate this in a good way. But the most important thing to do is to coordinate that level of action with proper protocols for collecting data and proper protocols for testing, and having systems for so those testing scenarios are multifactorial, they involve groups, The group sizes may change depending on whether you're doing it for a college campus or a school or for some other big enterprise. But there was no guidance on this, and that expertise does not reside at even the state levels, unless it's the larger states like California and New York and Massachusetts. And, you know, governors weren't getting any direction, and it was all panic mode.
Yeah.
They politicians, and they said, oh my God, I better shut down because you know, everybody's screaming at me from every side. And if they could have been protected by saying, we've got this task force is leading the way, it's telling us what to do. We believe in it, it's the science. But Trump's failure to set that up is the biggest failure and the biggest lesson that we maybe can learn from this whole enterprise, this whole sad story.
Yeah, the Swedish model was premised also on this idea of herd immunity, which is, you know, what did Trump call it? Herd intelligence. but it was, I'm wondering how much we know about immunity. I guess that's something you could figure in your model, but if it only lasts a few months, then what good is it? Could it still be powerful enough if we only needed to quarantine strictly quarantine a few months?
Yeah, so you can't know too much about it until you're well into individuals being immune and seeing the rates of waning and also antigenic drift. And so there are a number of things associated with that. And I guess the best information is, you know, what does immunity look like with regard to other COVID and related viruses? And that's the best information you have at this time. But everything points to the fact that you probably have several months of good immunity, and then it's going to wane. And is it going to wane over 3 years, 5 years, or 1 year? And that's going to make a big difference to whether you're going to have another outbreak in 2 years' time or only in 10 years' time. And the herd immunity is another interesting situation because it was clear that there's a highly structured age effect in this whole thing, and that asymptomatic individuals may be younger and asymptomatic individuals are not getting it as severely. And of course, to understand that, it will take time. But we didn't take advantage of that information either.
Thanks.
Thank you. I think this talk and Q&A was fascinating. We need to wrap it up, but maybe we can thank again Wayne Getz for this.
Okay, thank you very much. And thanks for joining us. And I hope to see you all in person sometime in the next year.